Hello YouTubers, and welcome back to the second part of this tutorial of hacking Megavolt for the Commodore VIC20. Now, we found the cheats in the earlier episode, and for most of us that is more than sufficient because we're playing these games on old emulators. The typings that we used to find in magazines, how would we create that today? Well, let's find out. I'm going to load the original cassette. Oops. And we normally just press play on tape. Obviously I'm using an emulator here, and I'm just going to speed things up a little bit so that we've got Megavolt is now loading. Okay, the program is loaded, but if we type list, we've just got a simple command, sys4352. Now that doesn't seem an awful lot given that we've loaded in around 24 blocks. 10 blocks is a leader. So this tells us that this is just a stub for basic, and we're going to jump straight into machine code. So again, we're going to jump into our monitor, and we want to have a look at address 4352. Now this is in decimal, and if we disassemble at 4352, we get the hex address 4352. There's not a lot going on here, so how do we get around it? There's a command that we can use called radix, and we'll just enter D for decimal, and then we can disassemble at 4352. Oops, you can't get the staff these days, can you? And this looks like proper assembly language, and the starting address is it's 1100 in hexadecimal. Now bear in mind that basic usually starts at around 1000 hex. Now that we know that that's the hex address, we could have converted that, but I'm going to put the radix mode back to hex, disassemble 100 to, let's just have a look at the first section of code. And it looks like we've got some initialization here for screen, etc. We've also got what appears to be a loader to set up the colours on the screen, and also to produce the splash screen that you can see. We can absolutely step and trace through this. In fact, what we'll do is, given that we've got initialization code up here, this I suspect is related to screen colours and the screen itself. We've got this final command here, jump 37A. Now that one does ring some alarm bells. We're going to set a breakpoint here at 1136, $1136. So the program will stop at execution. Now ordinarily we know that the start of the tape buffer is at $33C. So let's have a look at what's going on at $33C. Here we have an identifier, and then we have the load address. So this is the start address of the program that was loaded into memory, which is in little endian notation. So that would be 1000, which is obviously the start of BASIC, and we can prove that with 1000. And if you notice, we've got here the sys4352. Obviously the sys part is tokenized. But if we've loaded, how come we're jumping into the tape header? And this is where the developers were quite sneaky, and this is how some of the protection systems were first introduced. So within the header we've got the name of the program that was being loaded, which we saw up on screen. We've got a bunch of other information, And then at 37A, which is probably about here, we've actually got some loader code. Oops. And here we go, we've got some kernel routines, and you can refer to the VIC20 exposed book or any of the other VIC20 books for kernel explanations. But basically we're setting the logical block for the device, so number 1 for the cassette. We're setting the file name length to 0, and then we're calling load. And this will load in wherever the address is on cassettes, and usually the first 2 bytes of the cassette header is the actual load address. But what we have got here is break and a bunch of what appears to be JSRs, but they're actually just space. It's ASCII code for space. So something doesn't look quite right here, because we've called the load and then we're breaking, and then there's a bunch of essentially garbage. So what we're going to do is we're going to set another breakpoint here at 38 delta. Now then, we know that the code is going to execute at 1100, and we've already set the breakpoint up at 1136, was it? Yeah, 1136. What we can now do is, I'll tell you what we'll do. We will exit here, returning control back to basic, and type run, as we would have done ordinarily. And we can see here that the screen has already been blanked out, and it's all, there's going to be data there, I suspect. If we type in the SC command, this will produce the megavolt logo of that, I'm sure. So if we disassemble, we're at the next set of instructions to jump to 37A. So let's step. We're at D7A. Step. Now we've got the jump to subroutine at FFBA. And rather than trace that routine, we can just type in next. In fact, we'll just keep on doing next. We've got the jump routine to set the file name length to 0, so the first or the next file on cassette. It's obtained the header, I believe, so let's have a look. $33, sorry. Yeah, so we're loading in at 1000 again. Now then, if we disassemble this, the program counter is at 388. Sorry, so 388. We make jump to subroutine here, and that's still a break. So we're going to go next. We're going to call that subroutine. And here we have the splash screen as we'd expect to find. And I'm going to accelerate the code here. Okay, notice something odd. Remember 37A was the address that the basic program and the assembly eventually relinquished control to. We had that call. Oops, it's a bit slippy this mouse, isn't it? We had the call at FFBD and FFD5 to load the next segment in, but now the break instruction has been replaced with a jump instruction. 1010. Now, how did that happen? Given that if we have a look at $33C, the load address was actually at 1000 hex. Again, the developers injected a small loader routine into the tape header. So again, this was designed to fool us, and also to prevent us, or try and prevent us, from intercepting their code to inject cheats, etc. So let's have a look. We know that we're going to go to 1010, and again we've got some more screen initialization code, and we can trace this. There's various jump subroutines, or just the one here, and then we jump back into the cassette header at 37A, and that's at 1040. So we're going to put a breakpoint now at $1040, and we're going to resume. And we're going to allow the execution to jump, and there we go. We've got the screen initialized now. It's cleared the screen. It's got the loading message, and we've got stopped at 1040. We're going to jump back into the loader code at 37A. Again, it looks almost identical, except now we've got this jump at 1010, but I don't think that is going to stay. We still have a breakpoint at 38 alpha, I think. Oh no, 38 delta. We've got our breakpoint there. So what we're going to do is we're going to go next. You know the drill. I'm going to load the next section of code in. And look at that. We've now actually got the true execution address of the game, 361. If we disassemble 37A again, you can now see that the code has drastically changed, I guess, for want of a better word. Whereas we had the jump subroutines, that's now been replaced with new code, and 38 delta has been updated to jump to 361. So again, if we go to 3C, have a look at the memory there, we can see that the tape file name was still present, but now we've got more code loaded in. So again, developers use this as a way to fool us, or as a way to squeeze every ounce of available memory in a 3.5K machine. Let's have a look at what's happening at 361, which is going to be before the initial loader, and it's going to be somewhere around here. And again, we've got a bunch of initialization vectors before we jump into the main game here at 186F. So we know that what's happening here, but how can we inject our code? Well, if you also remember, we had the infinite lives at around $123. Now, where did this code come from? Again, it's probably best explained in that each of the headers of the cassette as it loads is a 2-byte address as to where to load the information. Now, at first I thought that this was a variation of modifying the load address on a cassette tape, but it isn't. In the second program, there's actually a piece of code that copies from main memory down to the stack. So page 1 is typically reserved for the stack, so 1FF working its way down to 100 hex. And as you can see here, here's our dec command that will decrement the number of lives. We need to create a loader. Now, given that we haven't got any space in memory really, because we've only got from 1000 or 1000 up to 1E00. And as you can see here, there's not enough space. We can't even put anything into the screen because again we haven't got any spare memory. So the developers used every ounce of memory that they can find. Seems like we're stuck, or are we? We can have a look at memory around 200, which is usually reserved for basic variables. So parsing tokens, I think the first 10 bytes is typically used for floating point calculations or floating point conversions. So what I've done is we're going to develop our own loader, and I've chosen memory address at 210. So how do we do the loader? Well, what we need to do first is we need to reset I'm going to hard reset, and we're going to clear all the breakpoints again. So delete break, no breakpoints are set. We're going to load the cassette in again. Jump back into the monitor, and we know that the loading code is going to start at 1100. So before we jump into the actual loader, we need to put a return statement here to return control back to our hack. And the return statement on RTS, we need to find the opcode for that. So we go back to our little table here, 6502 opcodes. We look for RTS here, and we know that it's $60. So we basically need to poke 1136 with $60. So we can assemble here dollar at 113C RTS. And there we go. We've initialized the screen, and then we're going to return control to our program hack. Now we know that at this point it jumps, or wants to jump to 37A, which is the loading code. I'm going to copy that because basically we're going to need to duplicate it. And in a Scratch document, we're going to put in the commands to assemble at 210, and we're going to put in the opcodes for a loader. Now we need to step back because we need to load the original program with the basic sys command in, and we're going to need this a few times. So we're going to call this routine 3 times, I think. And because ordinarily you can just use a jump subroutine and RTS, but we're going to save 1 byte and have a jump instruction there to $FFD5. Now unfortunately this doesn't support labels, so we're going to have to do this a little bit the hard way. So this is where we want to call. So at the moment we're going to put this at, let's say 2300. Jump subroutine, jump 2100 to load in this first program, and then we know we need to patch in at 113C the RTS instruction. So we're going to load accumulator with 60, the opcode for RTS, SDA at 113C. Now we can do the call to initialize the program as the sys4352 would have done. This will do for the moment. So what we will do is just check that we've got this to assemble and work correctly. So if we disassemble 210, we've already got our first mistake. We're jumping a subroutine back to ourselves, so that would just end up crashing. So 230, that's my mistake. It's always why we check these things through. So we're going to jump subroutine 230, which is our loader stub here. We're going to poke the loader code, the initial loader code, with a return address, and we're going to call it, and we're going to return control back to our program. Kind of makes sense? We don't have any further instructions yet because we need to find out what's happening after. We know that the code gets called at 1010 in hex. I hope this is all making sense anyway. It's kind of like my thought process. Okay. So what we're going to do is going to exit that, and we're going to reset again. We're going to take our template code, like so, and we're going to put a breakpoint at 218, break $218, because otherwise if we just let this run it will crash. Resume control back to basic, and then sys 528, and we're asked to press play on tape. This is now loading in the megavolt code, but it's under our control this time. And here we go. We're at the start of the jump subroutine 1100. So we can do this. We can go next. Oh no. What happened there? Something didn't go to plan, did it? So let's see what went wrong. Let's reset it. Let's assemble that again. We're going to load it again. Okay, so we're going to disassemble 1100. And I've set it at the wrong address. It's here, 1136. Just can't get the staff, can you? So let's fix our loader. We're going to reset again and start again. That's a nice thing about using an emulator. Exit, sys 528. Now this time, let's just check it. We've got our RTS before the jump. Okay, so next, screen will get initialized. And now we don't have any commands. So what we need to do is amend our code to have another jump subroutine to load in the next section. And we know that our program counter is set at 2 on B, so we can now type next, which will now load in the next portion. Now when we disassemble 37A, which is where the initial loader was, we've got the jump to 1010. So let's disassemble 1010. And if you remember, we've got some more screen initialization stuff before the jump to 37A at 1040. So we're going to amend our loader code to load A hash $60 again, store it at $1040 here. Then we're going to jump subroutine to $1010, and then we need to load the final piece of code. So we're going to add another JSR $230. Let's hope that we haven't got any overlap yet. Okay, now we've got the basic loader. At this point we should have the game code fully loaded, so we need to put in our cheat. So load A hash $05, and then I'm going to store that at $123. That's infinite lives. I'm going to store that at, can anybody remember? Nope. I'm looking at my notes now. At 118F, and we know that the game jumps in at 361. This should be all of our code. Now then, we've already hit another problem where we've overlapped code. So our jump instruction starts at 231 and our jump subroutine is at 230. So we need to modify our code now such that we know that the address here for this should be 234. So if I take this out completely, take that assemble out, instruction out, and reassemble it, here is our routine at 234. So we need to change all of the instances of 230 to 234. And now when we disassemble 210, we jump to subroutine at 234, which is our loader stub. Here we're setting the return statements at 1136. We're calling the program's initial screen, splash screen initializer. We're calling the next load, breaking into the program again, and calling its initialization routine. We're calling the loader for the final time to load the final part of the game. And now we're going to inject our cheats into the game. So we're putting the aura into infinite lives and infinite air. And then we're going to start the game as normal. And it's as simple as that. We've patched it. So we'll prove that this now works. We'll reset the game. Okay, and we're back into the monitor. We've assembled it for now. We're going to return control and now sys528. Press play on tape. We've still got the breakpoints enabled. And the game's loaded. And now if we press a key, we've now got infinite lives and infinite air. So how do we put this into a basic loader? I'm going to reset. We're going to go back to the monitor. Now remember our code that we assembled here. Now I'm going to have a look at the memory. In decimal, $210 to 247. Now this is our code in decimal. I'm going to go back to our notepad editor here. I'm going to start a new document and paste the data. I'm going to remove the data that we don't need here. Obviously use your favourite text editor, but this is one I prefer. And now where we've got spaces, I'm going to replace that with a comma. Like so. Get rid of these extra commas at the end. Now obviously we don't need all these extra zeros. There are smarter ways of editing it, but I'm going to do it old school. Don't need that final zero there. I'll tell you what, beats typing it all out by hand like in the old days. Doesn't hurt leaving those zeros in, but obviously it's a bit more typing for the user. And now we're going to put in here line 100 data. I'm going to copy that. There's faster hacks to do this, but it's only a short amount, so this will do for now. And we're going to modify that. 2, 3, 4. 7, 8, 9, 20, 10, 22, 23. So we've got a bunch of data statements here that can be used in BASIC. And next up we're going to need a header, and here's one I prepared earlier. The rem statement is obviously just to remind us what the cheat is. Restore to restore the data, and this is the poke that we're going to use. So memory address range 528 to 582. Remember, this is the basic workspace, so we have to be careful. We're going to read the data, poke the address with the data. This is just to clear the screen and set the cursor to home. Obviously in VIC20 you can press shift clear home with inside quotes to get the special character, but obviously we don't have that in our notepad, so it's a longer workaround. Ask the user to insert tape, press play, and then we're going to call our new machine code stub loader. I'm going to copy that, and then within the emulator hit paste. Might help if I resume. And look at that. Hey presto. The program has been typed in for us. And we can test this out with run. Oops. Press play on tape. I'm going to speed that up. Forgot about the breakpoints. There we go. And there you have it. Infinite lives, infinite air in an easily type-inable cheat. So what do you guys think? Leave a comment leave a message in the comments below. Thanks for watching.